Hey guys, it's Miss Beckham. Today we are going to go through types of reactions and the law of conservation of mass. We are using the notes that was posted under chemical reaction notes today, which today is October 13th. And I'm not going to go through every part of the slides because you do have them. I'm going to go through the parts that kind of I think need a little bit of a more thorough explanation. So just to start off with, in a chemical reaction, there are two parts of it. There are reactants and there are products. And so the reactants are on the left side of this equation, and the products are on the right side. And the arrow is what separates the reactants from the products. So reactants are what you start with, right? And products are what you end up with. So a good test question would be to identify the reactants and the products. H2O would be the product, H2 and O2 are the reactants, right? You guys have some notes on this, a collision model, factors that affect how fast a reaction can occur, the rate of a reaction, activation energy, catalysts. Read through that and email me if you have a question about that. I'm going to explain the types of a chemical reaction as well. So there are 6 basic types of chemical reactions that you will need to identify. There are certain ones that are redox reactions that we'll talk about what redox means later, and you should just identify, there's some notes and you can just draw an arrow and say these are redox reactions, right? But we're going to talk about the first one, which is a synthesis reaction. When you have a synthesis reaction, one product is formed. So you've got like an A plus a B makes a C, right? And so these letters, each letter represents a different element. So for example, H2 plus O2 combine to make H2O. And this is just a combination or a compound, right? H2O plus SO3 makes H2SO4. These two things are like an A and a B combining to form a C, right? And so A can represent an element, it can represent a compound, but one thing bound together plus another thing bound together reacts to make one thing bound together, all combined, right? That's a synthesis reaction. Two things or two or more things combining to form one product. A decomposition is reverse of that. So you've got one thing that breaks down into two or more substances. So this is your C if you want, or you can even look at it as an A, right? An A breaks down into something else plus something else, right? So you start off with one thing and it breaks down into different constituent parts. A single replacement reaction, basically this is a good overview of it, but what's happening in a single replacement reaction is that you've got, and I'm going to write it up here while I'm talking because it helps me to write while I'm talking. You've got one compound or one element, right? And then you've got a compound. So I'm going to change the colors here. You've got a B and a C, right? And then the reaction happens. And what happens is that A, I'm going to make A actually like a purple color. Actually, I'll make it a blue color. So we're going to make that blue, right? And A actually kicks out B, right? And so we've got this happening. And B now is on its own. It's all alone. This is a single displacement or single replacement reaction. You've got a compound in which one element has been bumped out. And the way this works is if let me look at this example right here. You've got zinc and HCl. So let's look at this. So zinc is like our A, right? H is our B. And then H ends up over here. So I'm going to go ahead and write that in. Zinc ends up right here. That's our A. And then chlorine is going to be our C, right? So what's happening here is that zinc bumps in and replaces H. And you might ask, okay, well, could you do it this way? Like, let's say that we have zinc. I'm going to make this black. You've got zinc plus HCl, 2HCl, the way that it is. Well, what if instead the zinc, instead of bumping out the H, could the zinc bump out the chlorine and make ZNH, right? This actually would never happen. So it would never happen. Zinc is a metal and it needs to go with the non-metal, right? Because the metals have a positive charge, and the non-metals generally have a negative charge. So when zinc bumps out something here, because zinc also has a positive charge, it's going to bump out the positively charged cation. And so it's going to bump it out, and it will form zinc chloride, ZnCl, and leave H all by itself. Okay, so this is an example of a single replacement reaction. This is the same thing happening here. You've got A, and then your A now is right here, right? I'm going to change this to a blue here. We've got our potassium, which is K. And then for C, I'll make that orange, which is our iodine. So what happens here is that chlorine replaces iodine. And that makes sense because when you look at where chlorine's location is, chlorine is a nonmetal that has a negative charge. Iodine also is a nonmetal with a negative charge. It's going to replace the iodine, not the potassium, because they're both negatives. It will only replace what it's like, right? Because potassium only bonds to negatively charged things. So it's going to bump out the iodine, right, and put it out over here. This is called a single replacement or single displacement reaction. The next type of reaction is called a double replacement. It's where you've got two compounds, right, and everything swaps. So, for example, let's look at K, and I'll fill in our A. K is our A with a positive charge, right? And then let's see where that goes. Now K is over here with the positive charge, right? And then we'll make a B. Iodine is our B with the negative charge, and it moves over here. Okay. We'll do purple now. Sodium is our C with the positive charge, and it moves over here. And then chlorine is our D with the negative charge, which moves right here. So if you notice, in a double replacement reaction, the elements swap with one another, but they swap in such a way that the positive is still with the negative, right? So you would never swap and put, like, for example, iodine is our B, right? And then chlorine is our D, right? This doesn't happen because they are both negatives, right? They're both nonmetals. And so you should end up with a metal, nonmetal happening over here, right? So just make sure that you're swapping them in such a way that positive is still with negative, but everything has been swapped. So for example, on this next one, I'll just do this. In this case, NO3 is like a polyatomic ion, and it acts as one thing, okay? And it moves over here. And then our D is chlorine. Our C is potassium, and it swaps, it's got a positive charge. And then our silver is our A. I think I did that in this color right here. That's a little bit of a different color, I think. And so that's how these swap. So your A swaps to go with your D, and the C swaps to go with the B. That's a double replacement. In a combustion reaction, hold on. In a combustion reaction, you're always looking for a certain thing happening, which is that if you see that in your reaction, you've got O2 on the reaction side, and then it produces CO2 and H2O, it's a combustion reaction. So you can recognize it very easily by seeing what's happening, okay? So if you have oxygen on the reactant side, and then it forms CO2 and H2O, it's a combustion reaction. It's very easily recognized. With a acid base, with a neutralization reaction, I'm sorry. What happens is that an acid and a base react to form some salt plus water. You can recognize acids because they normally have an H at the beginning. Okay. So this is an acid because it's HCl, right? NaOH is actually a base. We really haven't talked a whole lot about that. And they produce a salt plus a water, okay? Salt doesn't have to be just sodium chloride. There are different salts that generally are from like alkali metals, right? Alkali metals reacting with halogens, normally chlorine, to form a salt. But especially if you see water as a product and you see an acid, those are signs that it's a neutralization reaction. Redox reaction just means that electrons are being transferred. And there are certain ones that pointed out on these other slides that are redox reactions. It was on a slide up here. These are the ones that involve the exchange of electrons for these four right here. So you can look at that. So the next thing I want to get to is the law of conservation of mass. So I wrote this in here additionally. The law of conservation is based on the idea that matter can't be created or destroyed. It can only change form. So for example, if you have this reaction happening right here, in this reaction, we've got H, and there's two of them, right? Because it says H2. And then we've got O, and there's two oxygens. And then on this side here, we've got H, and 2 times 2 makes 4. So this big 2, which is a coefficient, multiplying times this little 2 makes a 4. And then O is 2 times 1, we've got 2. And so this reaction actually is not correct the way that it's written, because you can't create or destroy matter. So you can't start off with 2 H's and somehow come up with 4 at the end. So what we have to do is we have to balance this reaction to make it work. And so to balance any reaction, I'm going to write it down here. Here's how you'd balance any reaction. It makes H2O, right? You can put a big number in front to adjust the coefficient, okay? So you kind of tally everything up to begin with. So on this side, I've got 2 H's and 2 O's, right? And on this side, I've got 2 H's and only 1 O. And so in order to balance this reaction, that's what we're doing, to make this side equal to this side, because in reality, this reaction doesn't exist until we balance it. We can add a number that gets multiplied to make everything even. So I need this side to have 2 oxygens to be like this side. So I'm going to put a big 2 right here. That adjusts everything over here, because 2 times 2 now makes 4 H's, and 2 times 1 now makes 2 O's. And so now we've got 2 oxygens. That's good, right, on both sides. But now my H's aren't even. So I need to make this side now have 4 H's, and I'm going to do that by putting a 2 right here, because 2 times that little 2 now makes a 4. And there's nothing I need to do to my oxygens. They're already good to go. So I just can put a 1 right there. We don't need to change anything about it. This is balancing reactions. And if you can balance reactions and recognize types of reactions, you'll be good to go for today's lesson and really a lot of Thursday's lesson as well. So I'm going to work a couple extra problems here. So let's do this reaction right here. H2 plus N2 makes NH3. Okay, H2 plus N2 makes NH3. Okay, well, we need to tally up both sides to see if everything's good to go, or if we need to change something. And if we do need to change something, we can add a big coefficient here. So on this side, I've got 2 H's and I've got 2 N's. On this side, I've got 1 N and 3 H's. So we're not even, and I noticed a couple things. My N's are off and my H's are off. And I'm going to deal with H's first because it looks a little bit more complicated. So there are 3 H's here and 2 here. So we need to find the least common multiple between 3 and 2. So 3 times 2 equals 6. That's our least common multiple. So to get this side to 6 H's, I'm going to put a 2 right here, because 2 times 3 equals 6. Right? That also affects my nitrogen. Now I've got 2 times 1, so 2 nitrogens. So I've got 6 O's over here. I've got 2 over here. So I'm going to multiply by 3 to get this side to 6. This 3 only gets applied to the hydrogen because there's a plus sign separating the hydrogen from the nitrogen. And so now looks like I'm all even. I've got 6 and 6 and 2 and 2. So this equation is now balanced. Okay. One extra thing you need to know is that these molecules listed here, which you should write down in the notes that are attached, these always exist as doubles or diatomically. So if you have hydrogen just floating out around in space, it's always going to be a double like this, which means that technically it looks like this. There are 2 H's bonded together. So are all of these. They're always existing as a double. So when you have a reaction like this one right here, right, you would never have H plus N combining to form NH3 because N never exists by itself. It's always doubled. And H always exists doubled. And so that's why we put a little double there for each of them. Okay, so all of these you need to write down in your journal. That's the law of conservation. You need to know that the big numbers are coefficients, and that's what you're allowed to adjust. The little numbers are subscripts. You cannot adjust the subscripts. You can only adjust the big numbers. Okay, so here's some guidelines for you that you can follow. So one more example here of Na plus Cl2 makes NaCl, right? We need to balance this. So we're going to tally up both sides. On this side, we've got 1 sodium, and then we've got 2 chlorines because of this 2. And on this side, we've just got 1 of each. And so what we're allowed to do is adjust the coefficient in front. And so because this has 2 chlorines, I'm going to put, we have to adjust this. So I'm going to put a big 2 right here. That big 2 now makes me have 2 chlorines because 2 times 1 is 2. That also makes me have 2 sodiums because 2 times 1 is 2. So now it looks like I'm even, except my sodium now has 2 on this side. So I've got to put a big 2 right here to make it even. And that does not affect the chlorine because there's a plus sign in between. And so I can just put a 1 right here because everything else is good to go. That is essentially the law of conservation. And I want to work through a couple practice from today as well. So let me pull that up because I feel like the practice I went through with my students as well, some of the problems, because some of them were a little bit more difficult, more challenging. All right, so these are some ones that I went through with my students in class. I went through number 3, I'll do that, and I also went through number 9, okay? So for number 3, we're gonna tally everything up over here. We're asked to balance these equations. So on this side, I'm gonna just fill it in right here, but I'm gonna make my ink a little bit thinner here. And I'm gonna zoom in. Okay, so I'm gonna draw a line right here. On this side of the reaction, I have 1 carbon, 4 H's, and 2 O's. On this side, I've got 1 carbon, 2 H's, and 3 O's. So the reason I get 3 right here is because 2 plus 1 makes 3. You add them both together, okay? And so I need to balance it because it's not balanced right now. So what I'm going to do first is I know that my hydrogens are off, so I'm going to look at them. This side has twice as many hydrogens as this side. So I'm going to put a big 2 right here and then adjust what I need to adjust whenever that happens. So 2 times 2 now makes 4, and 2 times 1 now makes 2. Okay, I'm sorry, 2 times 1 now makes 2. So I've got 2 O's over here plus these 2 O's, right? So 2 plus 2, right? So that's 4 O's. So now I've got 4 oxygens on this side and only 2 on this side. And so now that makes it an even number. And I can put a 2 right here because 2 times 2 makes 4, right? And now when I look at everything, it should all be even. So I'm going to put a 1 here and a 1 here. Okay. See if that makes sense. And I'll go a little bit slower for this one right here. So this one's got parentheses, so I wanted to do it to show you guys kind of how It's just a more complicated one. So I've got aluminum, I've got nitrogen, I've got oxygen, and I've got sodium, and I've got H. It's a lot of stuff, right? So let's count all this up. I've got one aluminum, just one. And then the nitrogen in here is in parentheses. It's being multiplied times this 3. So 3 times 1 is 3. And then for oxygens in here, I've got 3 times 3. I've got 9 oxygens right here. And I've got 1 oxygen right here for a total of 10, right? And then I've got 1 sodium and 1 hydrogen, okay? So now on this side, I'm going to keep it in that order so that it's less confusing. So I've got 1 aluminum again. And then when I look over here, I've got 1 nitrogen. I've got 3 times 1 equals 3 O's over here plus these 3 O's. So I've got a total of 6 oxygens here. I've got 1 sodium, and I've got 3 times 1. I've got 3 H's. I think I counted up my O's wrong. No, I did. 3 times 1 is 3 plus 3 is 6. Awesome. Okay, so it looks like the main thing I need to focus on are my H's, my N's, and my O's. Sometimes you have to look at it and think, okay, which one kind of solves the most at one time? So I've got, I'm just going to kind of take a look at this. I've got 3 N's on this side and only 1 N over here. So in my mind, I know that I have to multiply this times 3. And I'm just going to play around and see if this makes sense. Because if there's 3 N's over here, I've got to multiply all of this times 3 to get this to 3 N's right here. So when I add that 3, now I have a different number of everything else right here. Now I've got 3 sodiums, right? I've got 3 sodiums, I've got 3 nitrogens, and now I've got 3 times 3, I've got 9 plus these 3, so 9 plus 3 equals 12. I've got 12 oxygens, right? Now when I look at this side, I've got 3 sodiums. I'm going to put a 3 right here because 3 times 1, it makes 3. I've got to put 3 over here. And so now I'm going to erase the ones that it applies to. Now I've got 3 sodiums, 3 oxygens. Well, I'm sorry, I don't have 3 oxygens. I've got 3 sodiums, right? And I've got 3 oxygens over here plus these 3. So now I've got 12 oxygens, right? And I've got 3 H's, okay? And as soon as I did that, everything else actually evened out. I've got 1, 3, 12, 3, 3, 1, 3, 12, 3, 3, okay? So those are some of the ones that I worked through in class. See if these make sense to you, try them, and then email me if you have any questions. We worked through 1 through 20 today, and then on Thursday, we're going to finish up by identifying the type of reaction that they are. All right, guys, email me if you have any questions, and have a great day.